everyone. My name is Cody Doucette from Raytheon BBN, and I'm here today to introduce you to Gatekeeper, the first open source DDoS protection system. I'm filling in today for Michelle Machado from HostNet, and also my colleagues Xiaobin Fu from Google and John Byers from Boston University. So our group started looking at this problem of DDoS attacks around 2015. And back then, we kind of had this feeling that DDoS attacks were rising in their complexity, magnitude, and frequency, just from bits and pieces that we could find throughout public sharings on the internet. Last year, we also found this image from Google, which shows a very clear trend in the largest known DDoS attacks. They break it down by bits per second attacks, packets per second attacks, and also HTTP requests per second attacks. And for each one of these metrics, the largest known DDoS attacks year over year is growing exponentially. So we found that this is a large problem, and it's a considerable concern for many network operators. And in particular, infrastructure layer or flooding attacks seem to be a big culprit here. So over just the past year or so these are the largest DDoS attacks from 2020, 3 of the largest providers have seen very massive attacks. Amazon saw a 2.3 terabit attack last February, which is close to the bandwidth record that's publicly known, which was 2.54 terabits per second back in 2017. And there's also been some very high packet per second metric attacks, some measured by Akamai and Cloudflare, that are reaching up to 800 millions of packets per second now. So we're approaching the problem from these bandwidth flooding attacks, infrastructure layer attacks, and thought to ourselves, how can we provide a solution for various companies, maybe that are smaller or medium-sized, to be able to defend themselves instead of maybe paying someone else to do the defense? And the solution that we came up with, Gatekeeper, we think is sort of a useful tool from 3 different perspectives. The first is that we're offering what we're calling unparalleled multi-vector protection. So at all times, all of the Gatekeeper filters that are used are active, and these monitor all flows in the system. This is kind of a crucial point, being able to keep state for every flow, which we define as a source and destination IP pair, because a lot of alternative solutions might be able to do some sort of filtering, but only with a limited capacity. And there's specific kind of attacks that make the defensive system kind of choose between implementing filters that are maybe too broad and induce collateral damage, or are very specific and too narrow and avoid or risk not actually mitigating the attack. Along with that multi-vector protection, Gatekeeper is scalable. Many of these infrastructure layer attacks are, in relative terms, fairly small, right? Less than maybe 10 gigabits per second. But Gatekeeper architecturally, and with a lot of the optimizations that are built into it, has the ability to scale. So we actually have a partner deploying Gatekeeper that's looking at a 1 terabit per second deployment. And that partner is mail.ru. And the last component of Gatekeeper that we think is especially useful is the fact that it can mitigate attacks in seconds. According to Kaspersky, more than 80% of attacks in the internet last for less than 4 minutes. And of course, this is not much time for human intervention, right? Being able to figure out what the attack is and where it's coming from, as well as deploying mitigating maneuvers. But for many attacks, Gatekeeper will mitigate those in seconds or instantly by virtue of the types of policies it enforces. So that was just a brief view into why we're in this space and what Gatekeeper can do. Now I'm going to get into more specifics about kind of the architecture of Gatekeeper and how it works. So the first main component of Gatekeeper that you need to understand are vantage points. Vantage points are these well-provisioned and geographically distributed points, ideally in a global deployment, located throughout the globe, as you see here. And these vantage points have 4 different requirements. The first is that they need some kind of compute capacity. So something like a bare metal server or perhaps even a VM. But in order to run a DDoS mitigation system, it can't really be done in like a dedicated router or something like that. The second requirement is that it needs cheap ingress bandwidth. You need to be able to limit the cost of the bandwidth that's coming into each one of these vantage points, because if you don't, you're going to give a lever to the attacker to be able to increase the price of your mitigation. The third requirement is to create basically an anycast network so that all traffic that's going to your protected destination is funneled through these VPs. And the typical way of doing that is using BGP peering. So all of these vantage points must support BGP sessions. And finally, the links between the vantage point all the way back to the protected destination AS should be private in some way. Now, this could be as simple as something like tunneling, or as complex or costly as something like dark fiber. But you want to be able to privatize that infrastructure between the VP and the destination network, and that just helps mitigate attacks against the routers and links on that path. So here in this picture, we have a set of vantage points along with a particular client that's trying to access the services inside of this protected destination AS. Each one of these vantage points we envision as being something like an internet exchange point, a peering link or peering hotel, or maybe even some cloud providers, particularly the ones that support BGP. This architecture is very similar to some of the solutions that are commercially available, but those commercial solutions have their own infrastructure to be able to implement this, right? They have their own edge data centers and points of presence. Here, we advocate for using shared infrastructure among the various stakeholders of the internet to be able to do DDoS mitigation and share some of the costs. So to deploy Gatekeeper, in each one of these vantage points, there will be a physical presence of some Gatekeeper components. So for example, this would require deploying a Gatekeeper server and actually connecting it to the switch of an IXP, for example. And once that Gatekeeper server is connected, it will announce the routes to the protected destination AS so that all traffic is forwarded to a Gatekeeper server. So when a client tries to connect or just send any traffic to the protected destination AS, the traffic is routed to the closest vantage point. And that's where the traffic is first handled by Gatekeeper. So here we're showing 3 Gatekeeper servers in parallel, but it could be as little as 1 for each vantage point. And the main responsibility of these Gatekeeper servers is to do upstream policy enforcement, right? So try to mitigate DDoS attacks as close to the source of the traffic as possible. So these responsibilities include forwarding requests. In our system, requests are the first packets of new flows. And those requests basically ask to allow this source destination flow to get some ability to just transmit packets to the destination AS. It's just requesting access. The Gatekeeper servers keep track of the decisions that are made about whether to allow this access and drop or rate limit traffic according to the decision that was made. The decisions come in the form of BPF programs. So each flow is assigned a BPF program and some small amount of state, about 64 bytes. And with that state and BPF program, we get flexible policies and software. So if a Gatekeeper server determines that the packets of a flow are allowed to be transmitted to the destination, it will transmit them at the established rate limit, but also encapsulate them along this path. When the packets reach the destination AS, they're first picked up by our grantor server, which is the complement to the Gatekeeper server. The grantor servers, the centralized place where all of this policy decision-making is done about which flows have access and at what rates. So the grantor's responsibilities include making policy decisions about requests and installing those decisions at Gatekeeper, as well as decapsulating those encapsulated packets from Gatekeeper and sending them to the ultimate destination server. Policies at Grantor are written in Lua so that you can more flexibly in software perform mappings between flows and what policies they should be enforced with at Gatekeeper. So to quickly summarize, packets from clients are forwarded to the closest VPs as a consequence of the Anycast network. Gatekeeper servers then take those packets and forward them, if they're new flows, to grantor servers. Or if they're an established flow with the decision already made, run a BPF program to decide what to do. Grantor servers for requests run a policy that maps flows to BPF programs and forwards granted packets to their destination. And whenever grantor servers make those decisions about new flows, they notify gatekeeper servers of what those policy decisions were. Then it's just up to the gatekeeper servers to enforce those. The crux of the system, though, and what can really sort of make or break a gatekeeper deployment is the accuracy and the definition of these policies. So next, I'm going to spend a little bit more time kind of diving into what it would look like if you were to write a policy for your network. So the first step in constructing policies for your own gatekeeper mitigation deployment is to identify all of the network profiles that you have. By profile, I mean some characteristics of a single server, group of servers, or just blocks of IP addresses that you can start to think, what are the characteristics here and how can I define them? So for example, consider an outgoing email server. Something like that is going to have no listening sockets, at least not ones that should be exposed to the outside world. And it's going to have a very small ingress traffic footprint. So from this kind of high-level description, we can kind of start to put together what are the ports that should be allowed here? What's the rate limit that should be allowed? You might be able to pull this information from various configuration files that you already have, the configuration of production servers, or some other documentation in your organization. Once you've established what your network profiles are, you can write BPF programs for each profile. Remember, BPF programs are basically software-defined policies that run upstream at gatekeeper servers. We recommend that each one of these BPF programs classify packets into one of 3 different bins. The first is a primary bin that has a kind of a baseline rate limit applied to it. And this represents packets that are sort of the main purpose of the service. Aside from that, though, we also advocate for a secondary bin, which consists of packets that are needed for the service to operate, but that shouldn't be present at the same kind of volume as the primary parts of the service. So for example, we need to allow TCP SYNs in, but we shouldn't be allowing them in nearly at the rate as regular traffic. Or similarly, we need to allow ICMP in order to diagnose problems with the network. But again, if we're seeing a large volume of that traffic, that's something unusual. So the secondary bin allows us to have a secondary rate limit for this other class of traffic. And finally, there's of course the bin of unwanted traffic. This isn't just traffic that you have to do an explicit detection of an attack on. This could be as simple as, for this network profile, I'm not allowing any of these ports, or I'm only allowing port 80. So anything beside that goes into the unwanted bin. So the primary bandwidth limit for the primary bin, that limit should be enforced before you try to classify the packet, because that's always your baseline. And then any secondary bandwidth limit happens after classification. Lastly, we advocate for a negative bandwidth enforcement policy. So typically, in a normal rate limit, when a flow runs out of credits for whatever time interval it's currently in, all of the packets will be dropped until the time interval is up, and then its credits refill. With Gatekeeper, you have the state to allow you to keep track of negative bandwidth. In other words, when a flow really misbehaves and sends it much past its allowed rate, then you can keep track of that and continue to drop packets until the flow backs off enough for its credit level to become positive again. This is a form of kind of real-time dynamic punishment of misbehaving flows. That's all kept per per flow. So once you've defined these BPF programs, then it's just a matter of mapping the flows to the BPF programs at grantor. The simplest way of doing this is just to classify flows using the destination IP address. So when grantor receives a new request for a new flow, it looks at the destination IP address and decides, Well, everything in this particular block that I know about, like the /25, for example, is for outgoing email servers. So assign it the BPF program that I've written for outgoing email servers. And remember that grantor servers run this as part of their policy, and it's written in Lua to be able to do things like keep track of longest prefix matching tables. You could go beyond just destination IP addresses when trying to classify new flows. You could also look at source IP addresses too. This provides easy ways of rejecting bogons or well-known abusers and malware, information that you could pull from various databases. But it also allows you to tune the allotted bandwidth for particular partners or for specific countries or end users, or return different profiles to entities like CDNs or crawlers or particular offices in your organization. If you want to get into this level of management, we've provided this tool called Drib, which is also on GitHub and just provides ways of kind of managing your IP address prefixes, merging them, prioritizing them, just organizing them as a whole. So you'd find it useful for your Lua programs. So that was a primer on how to write a destination policy. Let's now actually see kind of when, when all of this comes together, how an actual attack would be mitigated. Although we do have a couple of ongoing deployments, to evaluate this, we just set up kind of an experimental testbed on AWS. Because of some of the limitations of AWS, it's fairly small in general. It just evaluates up to 10 gigabits per second and just has a couple of packet generators that are forging 16,000 source IP addresses. While all of these attack flows are occurring, we also have a single legitimate client trying to upload a 20K file 50 times. So this kind of represents the worst case scenario for a legitimate client, right? Trying to upload a file when you're being bandwidth limited by a mitigation system during an attack. And the other components that you would need, right? A Gatekeeper server connected to a router that's connected to a grantor server, and ultimately the destination web server. So within this testbed, we just wanted to run some kind of simple policy enforcement programs and see what the effect would be. We found that even if we just do blind limits across attackers and across the legitimate client, that's still effective in mitigating DDoS attacks, right? We don't even have to try to pick out who the attacker is. Just by using kind of per flow rate limits, it's enough to allow the legitimate client to get through. Let's look closer at the data. So in the case where there's no defense at all, the black line here, the time that it takes for this legitimate client to upload that file increases exponentially. Even by around 5 or 6 gigabits per second, it times out and is unable to upload the file. So what happens if we put Gatekeeper in the picture now and direct all attack and legitimate traffic through Gatekeeper? The blue line here shows what would happen if you enforced a 32K rate limit for all of these flows. In that case, now the legitimate client is able to have some kind of bounded expected time in actual real time to upload this file, but it's limited by the bandwidth limit. So if we increase that bandwidth limit a little bit to 64K, or the red line, the time for the legitimate client to transfer that file now goes down to 4 seconds. Of course, if we keep increasing this limit, eventually we're going to be able to let enough attack traffic in that it's going to start affecting the destination server. So that's what you see with the green line at 128K. Now, starting at around 2 gigabits per second of attack traffic, enough is getting in to overwhelm the destination server and drive up the legitimate client's file transfer time. But remember that Gatekeeper in its flexible software policies has the ability to enforce negative bandwidth. So we also ran the 128 kilobit per second test, but enforced that negative bandwidth constraint. When this happens and attackers go beyond their credit limit and fall into credit debt, then all of their packets are dropped indefinitely, and the legitimate client is able to upload the file faster than in any of the cases that we measured. We also tested what would happen during a SYN flood. So the SYN flood test is a consequence of that secondary bandwidth limit. So recall that we have a primary for most of your traffic and a secondary rate limit for things like TCP SYNs. This is perfect for instantly mitigating a TCP SYN attack, because without a defense, the time that it takes for this legitimate client to upload a file increases exponentially. But with that secondary limit applied, most of the TCP SYNs from the attackers are now instantly dropped, and the legitimate client is able to instantly connect and upload this file. So now to conclude, I just want to review some of the future work that we're planning on doing in our project. So first, in order to enable cheaper deployments, right, in order to kind of combine all of this DDoS mitigation in as compact and as cheap of a package as possible, we want to be able to support the NICs with the highest capacity possible. So we're working on supporting 100 gigabit NICs at line speed. In order to enable a better return on investment for this kind of product, we also want to support load balancing and policies. We recognize that just having the resources to try to manage what essentially boils down to just a single DDoS mitigation service is more management than you're currently doing. So if we can include other applications like load balancing along with DDoS mitigation inside of Gatekeeper, we think you'll get a better return on your investment. And finally, we're thinking to the future in terms of the end game for attackers. In other words, trying to overwhelm enough of the infrastructure that even systems like Gatekeeper can't keep up with the number of flows. In that case, we're thinking of new ways of just trying to maintain some notion of fairness, even when keeping track of state and rate limits, these sorts of things, isn't possible. So to wrap up, Gatekeeper is an unparalleled multi-vector protection for DDoS mitigation. And this mitigation happens in seconds for an overwhelming majority of attacks. It's also scalable and open source. It's on GitHub, and it's ready for deployment. Finally, we have some very impactful features in store for the future. So please check us out on GitHub. It's at ultramajor/gatekeeper, or just search for Gatekeeper DDoS. And with that, we'd be happy to answer any questions you have. Thanks.
We have a few questions in the queue. The first question, how do we make sure these Gatekeeper servers don't introduce more latency to the network?
Yeah, that's a great question. So first of all, we haven't measured this explicitly. Our deployments are sort of in their infancy, but we actually went to sort of great lengths to make sure that Gatekeeper's performant and processing these packets quickly. In particular, we use DPDK, right, to bypass techniques, prefetching, batching. We use coroutines to try to make this as fast as possible. So like any on-path service, it's going to add latency, but we've tried to take steps to make that as small as possible.
You should expect a latency of less than 100 microseconds. So for most users, it won't be noticeable.
Right. Great, thank you for that. Next question we have in the queue. What prevents the DDoS attackers from simply targeting the grantor box itself as the weak link in the entire chain? Once that's down or can no longer communicate with the Gatekeeper boxes, no policy updates can happen to protect the target box.
Yeah, so the part of the architecture that's preventing that is the grantor servers in the protected destination network. But since we create an Anycast network through BGP announcements at the edge, all traffic, even that's trying to get to grantor servers, is directed first through Gatekeeper servers. So it will be mitigated there.
Yeah, we can also complement that the grantor server is not accessible outside of your network. So there is no way someone outside can send directly packets to the grantor. And on top of that, there is one aspect that is not covered in this presentation for the time limitations, is that only typically only 5% of all the traffic goes to the grantor, and that includes all the new flows that are being established. Once they are established, they are not necessarily go to the grantor some of the information in the presentation has been simplified, so you have a broad view of how the system works.
Great. Thank you for that. We've got 3 questions and 5 minutes to go through them. So fortunately, I don't think we can take any more questions. So I'll start with the remaining ones. The next question, in your blind limit slide charts, using negative credits would also degrade higher than typical client upload performance. Is that the correct read? AKA negative credits have the potential to degrade performance outcomes for some clients and uses if not carefully managed. Not saying this is a big problem, just a question to confirm.
Yeah, that's basically true. Although, as you mentioned there, those are blind limits applied for everyone, and there's nothing saying that those blind limits have to be applied that way. Grantor can make decisions about what traffic to grant and at what rates using anything it wants, right? It can pull from external databases. It can do some kind of learning. It can, look at reputation, and it can adjust at runtime as well. So those maybe lower limits would be applied to what it might perceive as attackers. But in the worst case, yeah, those kinds of limits might also hit legitimate clients.
Okay, thank you for that. Next question. How diversely do I have to deploy VPs in order to make the system useful? For example, does a single VP with a single grantor do me any good?
I think it can. Yeah, Michelle, do you want to take that one?
Yes, it does help. The need of a larger number of VP has to do with your user base. There is one paper that hasn't been published yet that we released that we were able to show that with 5 VP, not only you can have global coverage, but it's large enough to protect even against very advanced attacks like Crossfire. So although that paper was very generic, it points out that even a small number of VPs has a very large impact. And one of the small deployments that we have experience with, a single VP, if it has significant part of your traffic, it is still very impactful for the overall.
Okay, thank you for that. And this is our last question, and hopefully we'll be ending up right in time for next talk. Are there any concerns when traffic is asynchronous at a data center? For example, when it comes into data center A via Anycast, but the response comes from data center B?
Gotcha, great question. So there's not really any concerns in that case because the architecture is really one way, right? The Anycast traffic comes through the system, but the reverse path, it doesn't really matter which path it takes. For practical reasons, it's probably going to go back out through the same data center. At least that's been our experience so far, but there's no requirement for that to happen. And the system doesn't change in any way if that doesn't happen.
I can complement a little bit what Cody said about the system being one way, is that I would like to open your mind that the way the presentation was designed was to make it as simple as possible. But if there is interest, for example, to protect the other way around, meaning to your customers, for example, providing, let's say, a bandwidth for gamers, they want to be protected as the client, not as the servers. Gatekeeper could be deployed the other way around, so you can have both ways protection. But emphasize Cody's answer, there is no requirement from where the packets go out. They could go through the same path, reverse path, or any other data center.
All right. Okay. Well, thank you very much. That concludes your talk, and thank you again for your time with Cody, Michelle, and John, and appreciate the Q&A and the presentation.
Thanks all.